two elements.
Okay.
If one of those elements is a unit.
Okay, great. So there's our definition for irreducible. And this is a definition that holds in any ring. So we don't need division in order to do this, but we do want multiplication. Z is irreducible if and only if, whenever we write Z as a product of two elements, so Z is equal to, let's say, R times S, then the conclusion is that either R is a unit, so I should have said here Z belongs to a ring R. Either R is itself a unit or S is itself a unit. So we can't we can't factor. We can't write Z as a product of two things unless one of those things happens to be a unit. So let's just specialize that to a couple examples that are familiar and the ones that we're going to have to borrow from repeatedly over the course of the semester. Let's take, for example, let's take the integers. If R is equal to Z, then what are the irreducible integers? This is actually the content of 138 on here. But based on the definition that we have over here on the right, the only way to factor n would be if one of those factors is a unit. Well, what are the units in the integers? Right. The only integers that you can divide by in the ring of integers are plus and minus 1. So this definition for the integers would be saying that the only way we can factor an irreducible integer is to factor it such that one or the other of the factors is either 1 or negative 1. So what kinds of numbers are we talking about if we're talking about irreducible integers? We're talking about prime numbers on the one hand, though usually when we speak of prime, if we're a number theorist, usually prime refers to positive numbers. But irreducibility in this definition opens up one more possibility, a negative prime, and is either a prime positive number or the opposite of a prime. So for example, the number 17 is irreducible, but so would the number negative 23 be irreducible. Because the only way to factor either one of those two things is to factor out a 1 or factor out a negative 1. And since those are units, those are the only units, in fact, in the integers, that makes those irreducible. So in the case of the integers, at least, irreducibility is something familiar. It's just the idea of primality, but then permitting negatives as well as positives. The rings that we care about most this semester, though, are what kind of rings? Ultimately. Quadratic extensions are what we care about this week. But more generally, in the telling of our story of abstract algebra 2, what we care about most are polynomial rings. Now, we can get from polynomial rings to quadratic extensions through the procedure that we began this chapter with, through the quotient procedure. So there's a good chance that if we can understand what makes irreducibility in a polynomial ring, that we should learn what makes irreducibility in something like the quadratic extension of the integers. But let's, for the moment, think about a polynomial ring. And to make our lives easier, let's, instead of thinking about the ring as having polynomials with integer coefficients, let's ease up on ourselves for a moment and think about the ring of polynomials with rational coefficients, because the answer is a little bit easier here. So if R is that ring, the ring of polynomials having rational coefficients, then what are the units going to be? What polynomials satisfy the property written over here on the right? that if I were to write that polynomial as the product of two polynomials, that one or the other of those has to be a unit. Well, we can't understand irreducibility till we understand what the units are. And I think there was a problem in Chapter 1 that got to this idea. I think it may have even been on your homework. What are the units in a ring of polynomials over the rationals? Plus and minus 1. Okay, that's certainly, we can certainly divide and multiply by 1. All constants? Except for 0. So, in other words, the polynomial p equals 7/5 or something. That's a unit. How come? Yeah, p inverse is 5/7. It's invertible as a polynomial, as a constant polynomial, because it's invertible as an element of what? Yeah, as an element of the rationals. Every constant polynomial is nothing more, really, from an algebra standpoint, than just a single number in the coefficient field. And if that coefficient field is the rational numbers, then 7/5 definitely counts. So at least that justifies for us why the rationals are a subset of the units in the polynomial ring. So Q, the unit rationals rather, those non-zero rationals, are a subset of the units in the polynomial ring with rational coefficients. But why does it also go the other way? Why are they the only units? Why is it impossible to have an invertible polynomial with rational coefficients that's not constant?
Because you're never going to have an element of Q of t has another element of Q of t get you a degree of 0.
Okay, so there's a degree argument here, just to give yourself a flavor of that by thinking of an example. Let's take this non-constant polynomial, 2 plus t. If this were invertible, then what would have to be true? I would have to be able to multiply by some other polynomial over here, let's call it q, and the result would have to come out to 1. That's the definition of invertible, right? We have to be able to multiply by something that gets us back to the multiplicative identity of the ring, which is the same in q adjoint t as it is in q itself. That's the constant 1. But Emmanuel's making a degree argument, and take us through that one more time. So what are the degrees of the polynomials that we see here?
So you'll have degree of 1
I've got degree 1 here.
times degree n.
Times degree whatever. We don't know.
And that's going to equal, when you do that product, you're going to have degree of 1 plus n.
1 plus n. That was one of the theorems that was from, gosh, my citations are rusty, but you proved this on your homework. Oh, it's number 66. From your homework was this degree property, that when you multiply the degrees, when you multiply two polynomials together, their degrees add together. But then why is this an argument here?
Because we need it to equal degree 0.
Right. Because the multiplicative identity is a constant, in other words, a degree 0 polynomial. And so whatever the inverse of 2 plus t is, it's got to be a polynomial whose degree satisfies 1 plus n is equal to 0. And why is that not possible?
And that would be negative.
Right, not possible. Because, by definition, polynomials' degrees are always non-negative. By definition, the degree of q is greater than or equal to 0. And so that justifies why the inclusion goes both ways. And so any non-zero constant polynomial is a unit in the ring of polynomials with rational coefficients. So go back to the irreducibility graph. Which polynomials with rational coefficients, how will we decide? Maybe that's another way to go with this. I'd like to know, how are we going to decide whether a polynomial with rational coefficients is irreducible? It's not a question we'll be able to answer definitively today. We need a little bit more tools at our disposal for it. But let's see if we can decide on some examples. So here's an example of a polynomial with rational coefficients. I don't know, how about 2t squared plus 5t plus 1, or something like that. And I'd like to know, let me make this plus 3t. Let's go easy on ourselves. I want to know, is it irreducible as an element of Q adjoin T? Irreducible as an element of Q adjoin T, question mark. How will we know?
Because we can factor it.
Well, can we factor it?
2t plus 1 and t plus 1.
Okay. So check that we can indeed factor P in this way. And now that we've factored it, how can we tell whether or not P fits the definition of irreducibility that we have over here on the right? Because it's not just about whether it can be factored, it's also about the nature of those factors. What can we say about the polynomials 2t plus 1 and t plus 1 that will shed some light on whether P was irreducible? They're not constants. And if they're not constants, what does that mean? Yeah. If they're not constants, and they're not constants because they have degree equal to 1, not 0, and because of the statement underneath it, right here, the only units are constants. And so if these are not constants, then they're not units. And so what has that told us about whether P was irreducible as an element of Q adjoin T? It's not irreducible. It doesn't fit the definition because we factored it, and neither of those factors was a unit in the ring. So if we can factor, then that's a direct constructive way to prove that a polynomial is not irreducible. Things get a little more cloudy if we run up against a polynomial that maybe we don't know if we can factor. So, I don't know, let's be kind to ourselves here. Let's suppose we have P equals 4t squared minus 36. First I want to ask, as an element of the rationals, is this irreducible in Q adjoin T? There's the example I really wanted. 4t squared plus 36. Is this irreducible as an element of Q adjoin T? You're saying it's... It is? It is. Okay. So you think yes. But how do we know? Okay, so somehow, whether or not this is irreducible might have something to do with its roots. To the roots of P. This is going to be one of the themes of next week, because we'd like to be able to understand how far that observation can take us. Here, the observation that the roots of P are not rational, that observation turns out to be enough to justify why this is not, it is an irreducible polynomial. But we'll see some examples where that's not necessarily always enough. Actually, let's look at an example right now on why that's not always enough to get us where we need to go. What about t to the fourth minus 25. There's a polynomial with rational coefficients. Is it irreducible? I'm going to claim that it's not irreducible. How am I factoring this in my mind here? Factoring whizzes. T squared minus 5, t squared plus 5. So it's clearly, now that we've written down a factorization, we can clearly see that it's not irreducible. We can factor it into a product of two polynomials, and neither of those is a unit, because neither is a constant. But what do we know about the roots of this polynomial? T to the fourth minus 25. They're also not rational. We can say that they're, I mean, if we know what the real numbers are, we can say that plus minus square root of 5 are solutions. And if we know what the complex numbers are, we can say plus minus I times square root of 5 are the other two solutions. But whatsoever we call them, we can be pretty sure that none of the four roots of this polynomial are in fact rational. So one of the things we want to test out next week is how far can the observation of where the roots live take us toward deciding whether something is irreducible or not. So that's one point I wanted to make about this. The second point, going back to the example we were looking at a moment ago, 4t squared plus 36, I want to ask a slightly different question. I want to know, is this irreducible as an element of the ring of integers, the ring of polynomials with integer coefficients? So you decided that it was irreducible over the rationals in the ring of integers with rational coefficients. But what about in the ring of integers with, the ring of polynomials with integer coefficients? Remember, the question is, can I factor it in such a way that neither of those factors are a unit? So suppose you're working in math services, I don't know, with somebody trying to factor this polynomial. What options are you going to give them? We could factor out a 4, or 2, or whatever, but 4 is the greatest common factor between these two terms. I get 4 times t squared plus 9. What does that factorization do for us?
You have two non-units.
We have two non-units. Why are they both non-units? I mean, we can see why t squared plus 9 is not a unit, because it's not a constant. But now we're saying that 4 is not a unit? Why not? Exactly. Over here, the only units of z of t, as you showed on the homework, number 66, the only units of z of t are the units of c. In other words, the only invertible polynomials with integer coefficients are those constants that are invertible, and that consists of just plus or minus 1. So this factorization, 4 times t squared plus 9, it wouldn't have told us anything about the irreducibility over the rationals of our polynomial, but because 4 is a non-invertible integer, where it was an invertible rational number, it now counts. So this factorization counts in z adjoin t, where it didn't count in q adjoin t. So here's an example of something that factors over z adjoin t in a non-trivial way. But it doesn't factor over q adjoin t in a non-trivial way. It factors in the same way in both places. But in one sense, it's trivial, because 4 was a unit in the rationals. And in another sense, it's non-trivial, because 4 is not a unit in the integers. So I guess my point in stressing that so forcefully is to make the point that when you say the word irreducible, it matters how you complete that thought. It's not just irreducibility and factorability in a general sense. It's irreducibility in what ring? Because that question can change the answer, even for the same factorization of what counts and what does not count.